So we've learnt that when a massive, really massive star dies, there's no longer anything that can hold up its centre. It all collapses, forms a ball of neutrons, and in the process the rest of the matter rains down and bounces off. There's a huge flood of neutrinos coming out in an immense explosion. This is going to leave this ball of neutrons behind, isn't it?
Yeah, so the core of these stars collapse down, and you end up with the neutrons pushing on each other rather than the electrons. But the densities are insane. They are literally as dense as the center, the nucleus of an atom. So you get all sorts of funny effects. But the main thing is that you have literally a ball, maybe 5 or 6 kilometers across, that has the mass 1.4 times our sun. So the gravity on one of these, surface of one of these things would just be beyond anything you can imagine. Hundreds of thousands of times more than what we have on Earth. If you were to stand on this, you would be ripped apart by the tidal forces and flattened, as flat as, as you can imagine, a micron thick. Yeah. So it's a very extreme environment.
Yes, and the material underneath is so dense that if you could have a teaspoonful of neutron star material, it would have a mass equivalent to like a thousand of the Great Pyramid of Giza. That's the mass. The weight would be much, 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 much more than that because, of course, its gravity is so absolutely incredibly intense.
One of the interesting things about neutron stars is, although they're, they're very small and very extreme, you sort of expect most supernovae to produce one. And we have a lot of supernovae in the universe, one every second or so across the universe. And in our own Milky Way, we expect about every 100 years or so for there to be a supernova explosion making a neutron star.
So our Milky Way galaxy is perhaps 10 billion years old, so about 10 to the 10 years old. So if you're producing a supernova explosion every 10 to the 2 years, that means there should be 10 to the 8 neutron stars out there.
100 million neutron stars. So they're everywhere.
Yeah, so these are very common. And this was actually worked out right back in the 1930s. But the problem is, there's vast numbers of these things all over the place, but how could you see them? They're going to be so small, they're not going to shine. So back then people thought, yes, it'd be cool if we could see one of these neutron stars. There should be so many of them around there, but they're going to be really hard to spot. So people kind of gave up on the idea of actually observing these things.
One could imagine having a chance encounter, though. For example, one comes zooming by the Earth, and that wouldn't be very fun.
Yes, in fact, I set that as exercise for my physics students. Throw a neutron star through the solar system and see what happens, and it's not very fun, as you say.
Yes.
But indeed, you could easily imagine that these neutron stars would have been a purely theoretical construct. But then they were discovered much sooner than anyone would have thought in a totally unexpected way, and that's what we're going to talk about next.